Welcome viewers to this module 39 on the MOOC course on econometrics. In this module, we will take a look at two particular types of specification errors, namely omission of relevant variables and inclusion of irrelevant variables. So, we begin with omission of relevant variables. Let us consider the model yi being regressed on variables x2, x3 and an intercept beta 1. So, this we assume is the correctly specified model with all the properties of the classical linear regression model. Suppose that one variable is omitted. For example, x3 is omitted. So, the second line shows the incorrectly specified model. To distinguish between the two models, we may use the notation alpha 1 and alpha 2 instead of beta 1 and beta 2. So, the second line shows the incorrectly specified model and the first line shows the correctly specified model. So, this is the correctly specified and the second line is incorrectly specified. Now, we will see that if we use the incorrectly specified model to estimate alpha 2, then it will not give a true reflection of the corresponding parameter beta 2 in the correctly specified model. So, from the incorrectly specified model, we have alpha 2 hat is equal to summation yi xi in deviation form divided by xi square or yi x2i divided by x2i square. Substituting the value of yi from the correctly specified model, we have beta 2 x2i plus beta 3 x3i plus ui minus u bar, the whole thing multiplied by x2i summed and divided by summation x2i whole square. And expanding the numerator, we will find that we will have beta 2 x2i square summation, which will get cancelled with this x2i square summation in the denominator. So, that will give us beta 2 plus beta 3 summation. Take a look at the second term, beta 3 x3i x2i. So, this is x3i x2i divided by summation x2i square plus summation ui x2i divided by summation x2i square. It is important to note that this term in the middle is the estimated beta coefficient when the variable x3 is regressed on the variable x2. So, this is equal to beta 2 plus beta 3 times estimated beta when x3 is regressed on x2 and plus we have summation ui xi divide summation x2i square, ui x2i divide summation x2i square. And therefore, expected value of alpha 2 hat will be equal to beta 2 plus beta 3 and beta 3 2. So, what happens is, although variable x3 has been omitted from the model, it shows up through its correlation with variable x2. So, if x3 and x2 are correlated, then the omitted variable shows up through its effect via x2. So, therefore, this is not equal to beta 2 and that means the estimate is biased. So, the estimate that we get is a biased estimate. So, that is the basic problem if we omit a variable, but that is correlated with the variable that is correctly included, then the shadow of that omitted variable comes into the estimation, and the estimation procedure leads to a biased estimate. Next, we will see what happens to the variance. We will find that the variance also is affected if we omit the variable x3. So, the variance of alpha 2 hat, we know from our standard results of the simple or two variable model, variance of alpha 2 hat is sigma square divided by summation x 2I square. That is a very basic result that we have seen in the earlier modules towards the beginning. Whereas variance of beta 2 hat, which we would have obtained if we had correctly specified the model, would be sigma square divided by summation x 2I square corrected for the correlation between x2 and x3. And so, we see that this variance from the incorrectly specified model will be smaller than the variance that we would have obtained had we gone for the correct specification. So, there seems to be an apparent trade-off. Although the estimate is biased, its variance is smaller, but that is not the whole story. Reason is that the estimate of sigma square is given by residual sum of squares divided by n minus degrees of freedom. So, if we go for the incorrect model, it is RSS with 2 regressors divided by n minus 2. Whereas, if we had gone for the correct model, then we would have had RSS 3 with 3 variables divided by n minus 3. So, this is the correct estimate of sigma square hat. Expectation of this is equal to the true variance, whereas this is not. Expectation of this is not equal to the true variance. Therefore, it shows up that not only is the estimate biased, the estimated variance of the coefficient is also not correct. Therefore, the entire estimation procedure leading to t distribution or any other distributions, that gets affected. So, the entire estimation procedure is not correct if we incorrectly specify the model and leave out a variable which happens to be a relevant variable. Next, what we will see is how the estimation procedure gets affected if we overfit a model. That means, if we include variables that are not relevant. Now, let us take a look at what happens if we overfit a model. So, the correctly specified model has only one regressor, and the model which will be fitted has 2 regressors. This is an irrelevant variable which is incorrectly incorporated into the model. Basically, the results will be that even if this incorrectly included variable is in the model, the estimates of the actual coefficients will remain unbiased. So, alpha 2 hat from the incorrectly specified model is, as we know, yi x 2I x 3I square plus summation yi x 3I summation x 2I x 3I all upon summation x2i square summation x3i square minus summation x2i x3i whole square. Let us take a look at the numerator. So, we will substitute the correct value of y from the numerator. So, substituting yi, we will get beta 2 small x2i plus ui minus u bar, that is small yi, times x2i, and we multiply this with x3i square plus again yi, that is replaced by beta 2 small x2i plus ui minus u bar and multiplied by x2i x3i all upon x2i square summation x3i square summation x2i x3i whole square. So, let us look at the numerator closely. Beta 2 times x2i, again x2i. So, beta 2 summation x2i square multiplied by summation x3i square. So, substituting y in deviation form by beta 2 small x2 plus ui minus u bar, what we get is from here yi x2i. So, this is small yi x2i times x3i square minus small yi, this is small yi x3i times x2i x3i, and so collecting beta 2 terms together, what we have is beta 2 open second bracket and then x2i square summation of that, x3i square summation of that, and we also have beta 2 on this side. So, x2i x3i the product, again x2i x3i the product. So, you have x2i x3i whole square, and this term within the second bracket is exactly the term in the denominator. So, these get cancelled out and we come out with beta 2 plus we have the terms with ui, that is ui minus u bar x2i. Of course, u bar summation x2i will be 0 because x2i is in deviation form. So, this is ui x2i times x3i square minus again ui x3i times x2i x3i. So, the final result is alpha 2 hat is equal to beta 2 plus the expression in ui's. And of course, if you take expectation of alpha 2 hat, so expectation of alpha 2 hat will now be equal to beta 2. So, if we include an irrelevant variable, the estimates remain unbiased. However, the variance will be affected, as we can see by writing down the expressions for variance. So, variance of alpha 2 hat will be equal to sigma square divided by summation x2i square into 1 minus r square 2 3, whereas variance of the correctly specified model beta 2 in the correctly specified model, the estimate of beta 2 will be sigma square divided by only x2i square. So, from the incorrectly specified model, the variance of the estimated alpha 2 is going to be larger, because here we have 1 upon 1 minus r square 2 3, and r square 2 3 is less than 1, but greater than 0. So, this is a regular fraction. So, therefore, the variance from the incorrectly specified model, variance of alpha 2 hat from the incorrectly specified model is going to be larger. So, to sum up, what are the results of overfitting the model, that is including an irrelevant variable? Result is very nice, that is alpha 2 hat, the expectation is equal to beta 2, that means estimates remain unbiased, but the variance is now larger. Now, we will take a look at tests to detect whether a model is underfitted or a model is overfitted. Now we take a look at a test for adding variables. That is, if the correctly specified model has x, x square and x3, that means it is a cubic cost function, but the fitted model, that is the incorrectly specified model, only has x. So, this is a linear model which is incorrectly fitted in the case where the true model or correct model is a cubic model. So, how do we test whether we have actually left out relevant variables? That is called the Lagrange multiplier test for adding variables. So, the test is very simple. We run the restricted model. This is the restricted model because beta 4 and beta 3 are not there, xi square and x3, xi square and xi cube are not there. So, this is the restricted model. From the restricted model, we obtain the error of estimation. This EI is the error of estimation. Then in step 2, we run an auxiliary regression where EI is regressed on all the variables in the model, that is xi, xi square and xi cube. And we use a very important test statistic, that is we obtain R square, the square of the multiple correlation from the second step regression, that is the auxiliary regression, and then we use the test statistic, that is n times R square asymptotically follows a chi-square with q degrees of freedom. What is q? Q is the number of variables omitted. Here q will be equal to 2, and then if the calculated value of the test statistic exceeds the critical value of chi-square with q degrees of freedom, then we reject the null hypothesis, that is we reject the restricted regression and we go for the unrestricted regression. That means we go for the correct model. Next, we will take a look at a test where we will detect whether the model is overfitted. It is also very simple. So, we are modifying this and we are writing test for overfitting. So, test for overfitting. So, now this is the correct model and this is the incorrect model. So, the correct model has only x, the incorrect model has x, x square and x3. So, how do we detect whether the model has been overfitted? If you recall, the general format of this will be the correct model has only one variable, let us name it as x2i. The incorrect model has x2i, x3i and maybe x4i. So, yi should have been regressed on only x2i, but it has been regressed on x2i, x3i and x4i. So, supposing we want to test whether x3 and x4 are really incorrectly specified as the regressors. We are already familiar that we can carry out an F test for this. So, we will fit this model, this is the fitted model, and then you will use the F test. If you remember, the F test is F is equal to restricted residual sum of squares minus unrestricted residual sum of squares divided by the number of restrictions all upon unrestricted residual sum of squares divided by n minus k. So, here k is 1, 2, 3, 4, here it will be n minus 4 and the F distribution will have degrees of freedom q and n minus 4. So, we run the model and then we run the restricted model also and we calculate the F statistic as restricted residual sum of squares minus unrestricted residual sum of squares divided by number of restrictions all upon unrestricted residual sum of squares divided by n minus k, where k is the number of regressors in the unrestricted model, and we compare it with the critical value we compare this with f star q comma n minus k at the chosen level of significance. And finally, this will give a clear indication of whether we have overfitted the model or not. Actually, these F tests were done in detail when we studied the problem of testing of hypothesis. So, this is a very simple test, once again a repetition of what we had done earlier. We are actually testing whether these two coefficients beta 3 and beta 4 should be there or not. So, the null hypothesis is beta 3 equal to beta 4 equal to 0. So, the null hypothesis is H naught beta 3 equal to beta 4 equal to 0. That is, we write beta 3 beta 4 is equal to 0 0 and H1 is beta 3 beta 4 is not equal to 0 0. So, we compute this test statistic. If it exceeds the critical value, then we reject the null hypothesis, that is, reject this, and we say that this is not correct. So, that, viewers, concludes this module, where we have studied two basic forms of specification errors, namely omission of relevant variables and inclusion of irrelevant variables. Once again, to summarize the points, if there is omission of a relevant variable, then the estimate is biased and the variances are also not properly estimated. This is true when the omitted variable is correlated with the variable that remains in the model, and the test that we carry out is an LM test for detection. Whereas, if there is an inclusion of irrelevant variable, then there is no bias problem, but the variance again becomes larger, and this we can test by our familiar F test, or if you want a single coefficient, then you can use the T test. So, do go through the study material and please come back with any clarifications that you require. Thank you.